But this is a little bit weird because we want to make all the latent variables. So we want to make the distribution of all latent vectors follow normal distribution. But here the cost function or loss function, the meaning of the cost function and loss function is we want to make the conditional latent variable distribution for a given one single data point to be close to normal distribution with mean zero and identity covariance matrix. So this is a little bit weird and a little bit too strong cost function. Okay, so to make a unit zero mean and unit variance normal distribution, we don't need to all the conditional distribution make zero mean and unit variance. That is true. If we make all q pi z given xi for all I from 1 to n to be zero mean and identity variance normal distribution, then the mixture of q pi, essentially the q pi z distribution, is equal to sum of 1 over n I1 to n q pi z xi, because every distribution have the same property. We can say that because everything is just a random observation, so we can say everything has same distribution, right? So when we make everything follow normal distribution with zero mean and identity covariance matrix, naturally the q pi z as well. But this is too strong. There is some other distribution q pi z given xi that can make q pi z follow normal distribution, mean zero, and identity matrix. So more precise or more well-defined loss function may be this scale divergence between 1 over n sum I1 to n q pi z given xi and normal distribution, zero mean and identity variance, because we want to make this mixture of distribution close to normal distribution, zero, and unit variance. Okay, but the problem is computational complexity. If you have millions of data points to train your variation autoencoder, it is very, very difficult to compute. And essentially, to update pi for each iteration, you have to compute all single q pi value. So batch size should be full batch to compute this scale divergence. So this is kind of relaxation. Okay, forget about the mixture. Just focus every single instance and just make every single instance follow zero mean and identity covariance matrix. Right. But actually, although the cost function is scale divergence between q pi z given xi and normal distribution, zero and unit variance, q pi z given xi does not converge to the zero mean and unit variance normal distribution, because our cost or loss is combination of encoder loss function and decoder loss function. And here the decoder loss function, if the q pi z given xi follow normal distribution with mean zero and unit covariance matrix, since this latent variable distribution cover whole latent space, your output image is totally random. So with very high chance, the generated image is far from your target image xi. So your p theta xi given z with high probability will be very low. This is not desired property. So to maximize this log likelihood, to maximize this log likelihood, the decoder wants to make a q pi z given xi to be more narrowed and to be more specific, so that the z almost always can generate x hat value which is close to xi. Okay, from this combination of loss function, so make q pi z given xi does not convert to zero mean and unit identity variance. Okay, so this is the conceptual explanation of variational autoencoder. Actually, the variational autoencoder, the name comes from variational inference. So the concept comes from these equations. So basically, we want to minimize this log likelihood value minus log p theta xi, or maximize the log likelihood value. Okay. So this is very nice objective function. Basically, we want to make this line having high probability on all paths through this line. So on all single point, we want to make the corresponding probability is very high, and all this area has very tiny probability. That is what we want for the generative model. Then when you randomly generate a new data point, with very high chance the randomly generated point will locate it here. So we want to make the maximum, we want to make log likelihood to be maximized with decoder, latent variable with the normal distribution, mean zero, and identity covariance matrix. We want this. Okay, so from the log likelihood value, we can rewrite this log likelihood value using q pi z given xi concept. Since this is a distribution, when you take an integral with respect to z from minus infinity to infinity, if this g has multidimensional, then just let's say this is entire space. Okay, so this just multiply 1 basically, and then from this is equal to q pi z given xi log q pi z given xi p theta g given xi dz minus q pi z given xi log p theta g given xi q pi g given xi p theta xi dz. So here we just use log 1 is equal to 0. So when you look at this part is, sorry, here plus. This part is log 1. Okay, so we use log 1 equal to 0 to derive this equality. And when you look at this last term, the first part is KL divergence between q pi z given xi and p theta g given xi. and use the fact that p zeta z xi times p zeta xi is equal to p zeta xi given given z and p zeta z. When you use this fact, the second term is equal to minus k Lagrange q pi z given xi and p zeta z plus expectation with respect to q pi z given xi log p zeta xi given z. Okay. So this part was the objective function of variational autoencoder, what I explained in the previous page. And this part is some additional part that is a gap between the real log likelihood value and our VAE objective function. So when this value is equal to 0, then VAE, variational autoencoder, just maximize the log likelihood value as we want. But the problem is there is always some distance between q pi and p zeta for this conditional distribution. So variational inference means from many assumptions on q pi and p zeta, let's just assume that these two distribution is the same, and just make this part, the second part, to be maximized. Okay, and this is also called elbow. Since KL divergence is always non-negative, the log likelihood always bigger than this second part, the objective of variational autoencoder. So the maximizing the objective of variational autoencoder does not directly implies the maximizing the log likelihood, but in general, when you increase this second part, since this log likelihood value is an upper bound of our VAE loss function, when you increase the VAE objective function, then we can expect the log likelihood as well. Okay, and the elbow, the name elbow, comes from evidence law bound optimization, which basically, since this is evidence law bound, this is evidence, and this is law bound, and we want to maximize this law bound. Okay. Anyway, so VAE has these three, but essentially VAE want to make your latent variable follow zero mean and identity covariance matrix. That is the key of variational autoencoder, and that's why variational autoencoder is different compared to original autoencoder.